All right, let's see some examples of matrices on how to diagonalize a matrix. So the first example is a triangular matrix, and if you recall from the videos yesterday, the eigenvalues of a triangular matrix are simply the pivots. These are, so the two eigenvalues here are going to be lambda 1 equal to 1 and lambda 2 equal to 6. Of course, you could try to go the standard way of writing a minus lambda I and trying to find the determinant. You're going to get to the same result. Now we have to find the eigenvectors corresponding to lambda 1 equal to 1 and lambda 2 equal to 6. So when lambda 1 is 1, so this is the first case, then A minus lambda 1 times I becomes this matrix. I subtract a 1 along the diagonal, so I have 0, 5, 0, 5. Okay. Now the eigenvector of my choice, eigenvectors are infinitely many, but one eigenvector is, so you want this vector to be orthogonal to the rows of the matrix A minus I. Well, 1, 0 is the obvious choice here. Of course, any multiple of 1, 0 will do, any non-zero multiple. Now, case 2, when we substitute lambda 2 equals 6, we subtract a 6 along the diagonal. A minus 6I becomes negative 5, 5, 0, 0. So now we want another vector that is going to be orthogonal to the rows. Only the first row really counts. And that would be the vector 1, 1. This corresponds to finding special solutions for the null space. So remember from yesterday, this vector is in the null space of this matrix. Therefore, we need this matrix times this vector to give us 0. This matrix times this vector to give us 0. You can find these vectors by observation, or you can go the long route of finding the null space of this matrix, or finding a special solution for the null space. That will be this solution. Finding a special solution for that matrix will give you this vector. If you're able to do this by observation, great. If you can't do it by observation, by all means, use the algorithms for finding null spaces. So we have the two pairs, eigenvalue, eigenvector, eigenvalue, eigenvector, and we can write, with these eigenvalues and these eigenvectors, we can write two different diagonalizations for the matrix A. So we could write A equals what do we want? We want to say, AX equals X lambda. So from here you can write A equals X lambda X inverse. You can tell I don't know this by heart. So the matrix X in question, I would take 1, 0, 1, 1. Of course, we can switch places, but then if we do, we also have to switch the corresponding eigenvalues. So to the matrix X corresponds this matrix lambda, because the first column of X corresponds to the eigenvalue equal to 1, whereas the second column of X corresponds to the second eigenvalue equal to 6. So the matrix A, well, we want also the inverse. So this X is particularly nice because it's an upper triangular matrix. Its inverse is simply 1, 1, negative 1 here. Maybe you recall how to do this from elementary row operations. You can think of X as adding the second row to the first, and therefore subtracting it gives you the inverse operation. So X inverse is very easy here. And our matrix A can be written as 1, 0, 1, 1 times 1, 6 times 1, negative 1, 1 and a 0 there. And if I want to find any powers of a, let's say a to the k, I simply take 1 to the k and 6 to the k. So you see 1 to the k is just 1, whereas 6 to the k can be a very big number. Similarly from here, what if I wanted to find the inverse? You can still use this form of the diagonalization and put a negative 1 instead of k. So A inverse is 1, 1, 0, 1 times 1 over 1, which is 1, but then I have a sixth instead of the 6 because I have to take the reciprocals. That is the inverse of a diagonal matrix. And this is how I can find the inverse. So this factorization not only gives me powers, but I guess you could think of the inverse as a power, which is not exactly so, but you can make that generalization when you have this factorization. For other factorizations, that may not be the case. So factorizations of matrices are useful to give us different properties. Sometimes we want the LU decomposition, sometimes we want the QR decomposition, and sometimes we want the diagonalization depending on the particular application of a factorization. Now, if I wanted to change the order of the columns, I could, of the columns in X, I just want to remind you, I could do that. Then my matrix will not be upper triangular. It will, so I could take maybe a little detour here, just to make that other comment. So I could take, say, maybe I'll call that matrix Y, not to get confused. So we could take Y to be 1, 1, and then 1, 0. So this is not an upper triangular and it's not a lower triangular matrix. Then the corresponding lambda matrix, maybe lambda sub Y, I'll call it, will be 6, 1. And then for lambda inverse, I kind of have to think a little, for Y inverse, sorry. I have to think for a moment of what that is. You can calculate it using the formula with determinants. So the determinant of Y is what? 0 minus 1, so it's a negative 1. So I know that in my formula here, I have a negative in front of the matrix. Then 1 and 0 switch places. And 1 and 1, I think they switch signs. So let's see. Let's see how this will work. So if I take the first row times the first column, I'm going to get a 1. When I apply this minus inside the matrix, I'm going to get 0, 1, 1, negative 1. And quick check to make sure that we have, that when we multiply Y by Y prime, we get the identity. So first row of Y times first column of Y inverse gives me 1. First row times second column gives me 0. Second row times first column gives me 0. Second row times second column gives me 1. So that is the inverse. I can just quickly check. I don't remember formulas very well. So then I can also write the matrix A as 1, 1, 1, 0 times 6, 1 times 0, 1, 1, negative 1. So you saw that the first form was a little easier because we had an upper triangular matrix, although this is not that difficult either. So two different diagonalizations with these eigenvalues and these eigenvectors. All right. Now let's look at this example. This is an example of a matrix which is not diagonalizable. So this A is not diagonalizable. Now, I can give you a bunch of rules on how to decide if a matrix is diagonalizable or how it is not. But really, what determines whether a matrix is diagonalizable or not has to do with whether or not you can find enough eigenvectors. So when could you have trouble with finding eigenvectors? So in this case, it means not enough linearly independent, really, eigenvectors. This could only happen if you have repeated eigenvalues. So if your matrix is 2 by 2 and you have two different eigenvalues, then you will have two linearly independent eigenvectors. Eigenvectors that come from different eigenvalues are always linearly independent. We can prove that, but I just don't want to be bothered with the proof. But when we have the same eigenvalue, it could happen that the eigenvectors are insufficient, that you have only one eigenvector rather than two. So what's going on here? I could solve the determinant of A minus lambda I, or I could make some observations. Clearly, this A is singular. So immediately I know that one lambda has to be a 0. Then because this is a 2 by 2 matrix, I can just use the trace of the matrix to tell me what the other eigenvalue is. So I know that lambda 1 plus lambda 2 has to be the trace of A, and the trace of A is the sum of the diagonal terms, which is just 0. Now remember, lambda 1 is also 0, so it turns out that lambda 2 must also be 0. So what you have is two eigenvalues with the same value, and we call them repeated eigenvalues. And now the point here is that when we look at the matrix A, the null space of A will be the eigenvectors because the eigenvalues are 0. But the null space of A has only dimension 1 because the row space also has dimension 1. So we see that we can only find one linearly independent eigenvector. We cannot find enough eigenvectors. So the null space of A is where the eigenvectors are. And this null space of A, as you can see, is just span of the vector 1, 1. Since the dimension of the null space of A is 1, and you have the eigenvalue 0 repeated twice, so you wanted to have two eigenvectors, but since the dimension is only 1, we cannot diagonalize A. So the problem is not that the eigenvalues are repeated. The problem is that for that eigenvalue, there is only one eigenvector. This is the problem. So we call this repetition of the eigenvalues algebraic multiplicity, whereas the number of eigenvectors corresponding to that repeated value is called the geometric multiplicity. So here algebraic multiplicity is 2, but geometric multiplicity is 1, therefore A is not diagonalizable. You don't have to remember this algebraic multiplicity or geometric multiplicity. What you have to remember is that if you can't find enough linearly independent eigenvectors, you cannot diagonalize the matrix. That's it. Okay, now this example is very interesting. It's actually a solved example in the book and I'll upload that. But really, it's a very interesting example. I want us to diagonalize this matrix and see some interesting properties, and including I want us to find the inverse of the matrix from the diagonalization. But an interesting observation here is that this matrix is obtained as the difference of the following matrix. So I have, if I put 5s along the diagonal and I subtract a matrix of 1s, then I will get A. Right? Question is, why do we care? Well, let me call this matrix of 1s, say, B. This matrix is obviously 5 times the identity matrix. So I have A equals 5 times the identity matrix minus B. Why do I prefer to work with the matrix B than the matrix A? That's kind of the idea. The identity is always nice and easy to work with, especially with eigenvectors and eigenvalues. But what about this matrix B? So this is a rank 1 matrix of all ones. Let's suppose for a moment that it's very easy to work with B, and then I'll show you why it's very easy to work with B. We know that the determinant is 0 right away, and because the determinant is 0 and all the rows are the same, we also have, well, I'm gonna pause for a moment. Let's forget about B, everything about B except the fact that it's very easy to work with B in the world of eigenvalues and eigenvectors. So we like this B, and I'll show you why in a minute. But because we like this B, let's see how does that help us with A. So the key is the following. If X is an eigenvector of B with eigenvalue lambda, then X is also an eigenvector of A. The eigenvalue, so then X is also an eigenvector of A, but the eigenvalues are shifted. They're shifted by 5, so it's 5 minus lambda. Let's see why that is the case. So I have this assumption. X is an eigenvector of B with eigenvalue lambda. So this long sentence can be replaced with Bx equals lambda x. That's the assumption. I don't know about you, but I like this short form better. I can see it easier. Now, how can I check that X is an eigenvector of A? Well, I have to see what A times X is. So from here, I have A times X equals. Now, A is 5 times the identity matrix minus the matrix B. So I can replace that instead of A and multiply by X. Now I can distribute this multiplication. I have 5ix minus bx. Well, I times x is just x. Identity times x doesn't do anything to x. It's just x. Whereas b times x is lambda x. So we have 5x minus lambda x. 5 is a number, lambda is a number. So I can factor x, whether on the right or on the left really is irrelevant because we're dealing with numbers. But I have 5 minus lambda times x. So in summary, a times x is 5 minus a lambda times x. So you see, this is very important. This is the proof of the statement in words, why it's true. So if I can find, and this is for any eigenvector of B and for any eigenvalue or the corresponding eigenvalue, right? So if I can find the eigenvalues of B and the eigenvectors of B, then I immediately have the eigenvalues and the eigenvectors of A. And that is powerful. It is powerful because it is very easy to find the eigenvalues and eigenvectors of the matrix B. And I'll show you what they are. So here's our matrix B. The first thing in trying to find the eigenvalues and the eigenvectors is, well, to find the eigenvalues. So what do we know about the eigenvalues of B? Well, we know that lambda equal to 0 is an eigenvalue because B is invertible. Oh, sorry, singular. Because B is singular. Now, the question here is, how many times lambda equal to 0 is actually an eigenvalue. Like, what is the multiplicity of that eigenvalue? And you see, this is where the comment of geometric and algebraic multiplicity can help us a little bit. Of course, I can prove this by just solving the determinant and showing you what it is, solving the determinant of b minus lambda I. But I could also use the fact that the null space of B has dimension 3. So you see, if I reduce B, so I do row 2 minus row 1 into row 2, row 3 minus row 1 into row 3, row 4 minus row 1 into row 4, what do I get? I get 1, 1, 1, 1, and then a bunch of zeros. We know that the dimension of the row space plus the dimension of the null space must equal 4. So we actually see that we have one pivot column, we have 3 free columns, right? x2, x3, and x4 are free columns. So the dimension of the null space is 3. So because the dimension of the null space of B equals 3, we know that actually lambda 1, lambda 2, and lambda 3 are all equal to 0. Okay. Because you see, if you don't, the geometric multiplicity cannot be bigger than the algebraic multiplicity. The algebraic multiplicity tells us how many times 0 is a repeated root. So geometric multiplicity cannot be greater than algebraic multiplicity. So we cannot have a lambda being a repeated. You see, if we have, let me put it this way. Let's say we have 4 different eigenvalues, or we have a lambda 0 once, and then different values are for, we have 3 different values, or values different from 0 3 times. Then they would give us different eigenvectors. Every time you have a different eigenvalue, you get different eigenvectors. So the fact that lambda equal to 0 results in 3 linearly independent eigenvectors, it tells you that you must have that 0 as an eigenvalue 3 times. We don't have to worry about proofs, but that is the case. So we have x1, for example, equal to, and please forgive me with uses of x's. Maybe I'll remove these because those x's and the x's I'm writing here are not the same thing. So I need to find the 3 special solutions to this matrix with the null space. So I can put 0, 0, 1, negative 1. So that's by setting the second variable to 1, everything else to 0, or the other 2 to 0. Then I have 0, 1, 0, negative 1, and then I have 1, 0, 0, negative 1. So these are the 3 special solutions for the null space of the matrix B. Now, how can I find the 4th eigenvalue? This is the point. So 3 eigenvalues are 0. I want to find the 4th eigenvalue. It's very easy. You have lambda 1 plus lambda 2 plus lambda 3 plus lambda 4 is equal to the trace of the matrix B, and the trace of the matrix B is simply 4. Since all of these are 0, you see that lambda 4 must be a 4. So lambda 4 equals 4. To find the eigenvector corresponding to this value, I have to subtract 4 from the diagonal of B. And what I will have is 1 minus 4 is a negative 3, and everything else is a 1. Now, I know that I can only find one eigenvector. I know that this matrix is of rank 3 right away. So really, I could look at any three rows and try to eliminate. I see that but at the same time, we just want one vector in the null space of B, right? This vector, sorry, it shouldn't write B here, my bad. This is B minus 4i. Okay, so the matrix B minus 4i is what I have here, and I'm looking for a vector in its null space. And it's very easy to see that if you just add up the 4 columns, you're going to get 0. The sum of the 4 columns adds up to 0. So I see that the last eigenvector is just 1, 1, 1, 1. And you see, anytime you have a matrix of the form B minus some number times I, you will always have this eigenvector. So this is very powerful. We actually know the eigenvectors easily for a matrix of all ones because it was a matrix of all ones, nothing special. So whenever you can express a matrix A as some multiple of the identity matrix plus or minus a matrix B, so you could have had here all ones and then fours, then you would have said this is 3 plus this matrix. The point is that the eigenvalues and eigenvectors of B are fixed. They are what they are because this is a matrix of all ones. But then for A, we are going to have to adapt. So we know that the eigenvectors that we found for B are also eigenvectors for A. We showed that right here. And we know that the eigenvalues corresponding will have to be shifted. They will be 5 minus lambda. So right away, we know that the matrix X for A, right? Well, also for B. So that matrix, the eigenvector matrix is the same for both of them. So we had negative 1, 0, I think it was, no, negative 1, 1, 0, 0, then negative 1, 0, 1, 0, and then negative 1, 0, 0, 1, and then finally 1, 1, 1, 1. By the way, I mentioned yesterday, if you have a symmetric matrix, the eigenvectors are orthogonal, and you can see that the eigenvectors here are orthogonal. The corresponding lambda matrix, from the order of how I wrote the eigenvalues, the eigenvectors will be 0, 0, 0, and then a 4 here. Sorry, my bad. Those would be the values for B. For A, so I'm going to write this lambda for A, I have to use this rule that the eigenvalues are 5 minus lambda. So I'm going to have 5 minus 0, 5 minus 0, 5 minus 0, and then 5 minus a 4, right? The last eigenvalue was a 4. So really, we have 5, 5, 5, 1. And you can test this. You could multiply A times any of the columns of X. So you could try A times this first column and see what you get. You should get a 5. If you don't have a 5, then we have a mistake somewhere. All right, so that is X, that is lambda. So I want to make another comment here. Because the columns of X are mutually orthogonal, if you note, well, sorry, they're not mutually orthogonal. I guess I could orthogonalize. They're orthogonal to the last one. Doesn't matter. So we have the matrix A, which equals X lambda X inverse for this X and for this lambda. If we want to find powers, then obviously A to the K will equal X lambda to the K X inverse, We can also find the inverse of the matrix. And interestingly enough, you can, I guess there are better eigenvectors that we can find for the matrix A, where we actually have orthogonalized, we have orthonormal columns, or we can have an orthogonal matrix X. I did not do that. But ultimately, I will just write what A inverse is. You can work a little bit on this to show that it is so. But A inverse is 1/5 of a similar matrix. 2, 1, 1, 1, 1, 2, 1, 1, 1, 1, 2, 1, 1, 1, 1, 2. So it's actually identity. So 1/5 of the identity plus the matrix B. So this is 1/5 of the identity plus B. And let's quickly check that this really is so. How can we do that? Well, we can do A times A inverse and make sure that this is the identity. So what was our rule for A? We had 5 times the identity minus B. And then A inverse, we claim, so let's just check that this is really so. We claim that it is 1/5 of the identity plus B. So this 1/5 can go to the left. We don't have to worry about it. And then we have to take the multiplication. So we have 5 times the identity times the identity. Well, identity times identity is identity again. So we have 5 times the identity matrix. Then we have 5 times the identity times the matrix B. Well, identity times B is just B. So this gives us 5 times B. Then we have negative B times the identity. So that gives us negative B. And then we have B squared. So we have to think for a moment, what is B squared, right? How can we figure out B squared? Well, we have X and we have lambda. We have lambda for I, but lambda for the matrix B will simply be 0, 0, negative 4, right? So, sorry, not negative 4, but positive 4. So let me say the matrix B is the same X that we found for A times 0, 0, 0, 4 times X inverse. So B squared will be X times this matrix squared, which will be 0, 0, 0, 16 times X inverse. So I guess I do need X inverse. Okay, this proved a little harder than I thought. This part over here will simply be 16 times the last eigenvector. So that one, well, and a bunch of zeros. So that part of the matrix is just 0, 0, 0, and then 16, 16, 16. And then I need X inverse. Which I really don't want to be calculating from over here. It wouldn't be too hard, but it's work to be done. Or maybe there is a better way to do this. Let's expand here. So let me simplify this. What is this? This is negative 4b minus b squared, which is going to be, say, minus b times 4 times the identity minus b. Is that helpful? So I can calculate this rather than 4 times the identity minus b. No, that doesn't come here. Okay, I guess I'm gonna stop here. You guys can continue these calculations. I don't want to be taking powers of matrices. I think there was an easier way to show this, but I obviously did not check it. So I apologize for that. There are better ways. If you have a better matrix X, we can orthogonalize the matrix X, make sure we have orthonormal eigenvectors. It is possible. And then it will be much easier to do all these computations. Anyway, I'll stop here. I know I quit on this problem, but after quitting, I actually saw the solution. So the idea here, remember, we're trying to show that this product is the identity. Well, clearly 1/5 of 5i is the identity. So what we're trying to show is that the rest here is 0, and that's not difficult to prove. So 5b minus b is 4b, even though previously I had written minus. So I have 4b minus b squared, and I want to show that this is 0. I will rewrite that as b minus b times b minus 4i. So I'm just switching the places here. I'll factor that minus, and then I have this matrix. So I want to know what is b times, b times 4 times the identity. Was it 4 times the identity? No, b minus 4 times the identity. What is this? Well, I actually have to look into the matrix B and the matrix B minus 4 to the identity, 4 times the identity. So I will copy our matrix B. And let me copy our matrix B minus 4 times the identity. All right, so again, some copying here. That is the matrix B, and this is the matrix B minus 4 times the identity. Now, I'm not gonna write 16 more zeros, but it's not easy, it's not hard to see that this has to be the 0 matrix. Why is that? Well, this row times this column, when you take the dot product, it essentially means add up all the terms in the column. So this times this is 0. Similarly, this times this is 0. Similarly, this times this is 0. This times this is 0. In fact, if you recall, I could also put this b on the other side. The eigenvalue, this vector, a vector of all ones, was an eigenvector for this matrix, which means it is in the null space of that matrix. And perhaps that is the better way to write it. But either by observation here, or you could just say b minus 4 times I times b. So look at this product, where you first have this matrix over here, and then you have the other matrix. You see that the columns here, each column of this matrix is in the null space of that matrix. If you remember here, we found the null space. So this vector x4, which consists of all the ones, is in the null space of b minus 4i. So when I look at this product here, every column in B is in the null space of this matrix, so I know right away that I'm getting zeros everywhere. So I'm getting 0 here. Okay. Not as a number, but as a matrix. So going back, I see that all of this is 0, and I am left with the identity matrix. So we can just check that this is indeed the inverse by doing these computations. Although if you want to use a diagonalization, there are better diagonalizations than X. for this matrix, although I can't really expect you to be able to find them, so don't worry about that. All right, now we're definitely done.